Welcome back to the next lecture. We are still looking at water, but this time around we are looking at water as a reactant. Okay, water as a reactant. Okay, we have been looking at the physical properties of water. Now we want to look at how water participates in various chemical reactions within the cell. Right, if we look at water, okay, water has a tendency of dissociating. Okay, water has a tendency of dissociating. Okay, once it dissociates, it will produce a hydrogen ion, and of course it will produce an hydroxide ion. Okay, however, the extent of dissociation is very minimal, very minimal. Okay, right, but it has the tendency to dissociate as is given in the diagram above. So if you calculated the equilibrium constant of this reaction, we know that the equilibrium constant is calculated by multiplying the concentration of the products. So the products is hydrogen concentration, concentration of hydrogen ions, and concentration of hydroxide ions, divided by the product of the concentration of the reactants. In this case, the reactant is water, so the concentration of water. That gives you the equilibrium constant of this reaction. Now, for pure water, okay, at a temperature of 25 degrees, this equilibrium constant has been calculated and has been found to be, okay, experimentally this has been found to be equal to 1.8 times 10 to the power minus 16 moles per cubic decimeter. This is an experimental value. This is what has been found experimentally when you do it in the lab. Okay? Right. Now, if we said that, let's cross multiply this. Okay? Cross multiplying, if you cross multiplied, then it will be equilibrium constant multiplied by the concentration of water. Okay, this will give you the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. Before we actually insert in the values, let's try to calculate the concentration of water. Okay, let's try to calculate the concentration of water. Okay. Okay, so if we are to calculate concentration of water, okay, we know that concentration, which is concentration of water, is given by the moles, in this case the moles of water, divided by the volume of water. The volume of water. Okay? That is how we calculate concentration. Now, if we assume, okay, Okay, my markers are getting used up. If we assume that you have 1 liter of water. If we assume that we have 1 liter of water, let's try to calculate the concentration of water in 1 liter. Okay? So we know that the density of water, okay, the density of water is 1 gram per mil. Okay, per mil, not per mole, but per mil, milliliters. Therefore, if we have 1 liter, which is equal to 1,000 mils, okay, then it follows that the mass of water in this case, mass of water is equal to 1,000 grams. 1,000 grams. Okay? 1,000 grams. Just in case there is someone who's not following, if there is someone who's not following, this density, going by the density, 1 gram will be contained in 1 mils of water. 1 mil of water. Now, if we have 1,000 mils of water, how many grams of water will be contained therein? So if you cross multiply, then we are saying X will be equal to 1 gram times 1,000 mils divided by 1 mil. So at the end of it all, it gives you 1,000 grams. So the mass of water in 1 liter is equal to 1,000 grams. Okay. If that is the case, then we can say the moles of water, okay, therefore, moles of water is equal to, we know moles is equal to the mass that you are dealing with divided by relative molecular mass of that substance. In this case, we are dealing with 1,000 grams divided by the relative molecular mass of water is 18 grams. You can work that one out. Water has 2 hydrogens and 1 oxygen. Oxygen is 16 grams. Hydrogen is 1. 1 times 2 is 2. 2 plus 16, that gives you 18. So this will give you 55.5 moles. These are moles. Okay? These are moles. These are moles. Okay? Those are moles. Okay? If that is the case, and then we come back here, okay? If that is the case, okay, we can then say, what can we say? We can then say the concentration of water, okay, concentration of water is equal to moles of water over volume of water. Okay, so moles, we've calculated 55.55 moles, but we said that the volume is 1 liter. So we can say 1 liter, remember 1 liter is equal to 1 cubic decimeter. Okay. So the number of moles then becomes 55.5 moles per cubic decimeter. Okay. Per cubic decimeter. Right. Now, going back to our equation that I gave you earlier on, we did say that the equilibrium constant of water, okay, multiplied by the concentration of water gives you hydrogen ions multiplied by hydroxide ions. Okay. Right, so we said that this is experimentally found, and it has been found to be 1.8 times 10 to the power minus 16 moles per cubic decimeter. Multiplied by concentration of water, we've just found it to be 55.5 moles per cubic decimeter. This is equal to concentration of hydrogen ions in water and concentration of hydroxide ions in water. Okay, so if you do the calculations, this value will give you 1.0 times 10 to the power minus 14, okay, moles squared per cubic decimeter squared, so we can say 6 if it's squared. This gives you concentration of hydrogen ions multiplied by the concentration of hydroxide ions. And okay, this equation, okay, is called the ion product of water. The ion product of water, which is very, very important. We must know it. The ion product of water. It tells us that if you multiply the concentration of hydrogen ions in solution and the concentration of hydroxide ions in solution, it will give you 1.0 times 10 to the power minus 14 moles squared per cubic to the power per decimeter to the power 6. Okay, this is called the ion product of the water. Very important equation which we must know. We must keep it in on our fingertips. Very important parameter to use. Okay. So let's assume, okay, that we have pure water. In pure water, okay, we have pure water. In pure water, concentration of hydrogen ions will be equal to concentration of hydroxide ions in pure water. If that is the case, let's substitute hydroxide ions with hydrogen ions. Let's eliminate hydroxide ions in the equation. Since hydroxide ions is the same as hydrogen ions, where there is hydroxide ion, we can put hydrogen ions. So then this gives us 1.0 times 10 to the power minus 16 moles squared per decimeter to the 6, which is equal to concentration of hydrogen ions multiplied by by hydrogen ions again, because we are saying hydroxide ions are equal to hydrogen ions. Okay, so we can then say 1.0 times 10 to the power minus 16 moles squared decimeter to the 6 is equal to hydrogen ions squared. Okay, we can then find the square root both sides. So we can say square root of 1 0.0 times 10 to the power minus 16 moles squared per decimeter to the 6 is equal to square root of hydrogen ions. Okay? Of course, this is squared. Okay? If you do your calculations well, this will give you 1.0 times 10 to the power minus 7 moles per cubic decimeter is equal to the concentration of hydrogen ions. Okay, I hope you are able to see. Okay, praying that you are able to see. My marker is behaving. Okay, so this is 1.0 times 10 to the power minus 7 moles per cubic decimeter. If you can see from your analytical chemistry, that's a concentration unit, moles per cubic decimeter. Okay, moles per cubic decimeter. Okay, conversely, we can say that if we know the concentration of hydrogen, from this statement, concentration of hydrogen is equal to concentration of hydroxide ions. So it follows that if the concentration of hydrogen ions is 1.0 times 10 to the power minus 7 moles per cubic decimeter, this should be equal to the concentration of hydroxide ions. Okay. So these are indicating concentrations of hydroxide ions and concentration of hydrogen ions in solution, okay, in water particularly, okay, in water. Okay. Right. Now, what is key to note? Okay, what is key to note is that we have said pure water has the concentration of hydrogen ions equal to the concentration of hydroxide ions. That's pure water. Okay. If it's not pure water, it's water in which other solutions have been dissolved or other solutes have been dissolved. It will not be pure. You may have more hydrogen ions or you may have more hydroxide ions. I will repeat what I have said. In pure water, the concentration of hydrogen ions are equal to the concentration of hydroxide ions. But if in water we put a solute, which could be a solid or a liquid, okay, it will no longer be pure water. But it will be such that maybe the concentration of hydrogen ions will be more than the concentration of hydroxide ions. Or you may have a scenario where the concentration of hydroxide ions are more than the concentration of hydroxide, of hydrogen ions. Okay? If that is the case, if the two are not equal, okay? If the two are not equal, if in a solution you have more hydrogen ions, then we say that the solution is acidic. Okay? On the other hand, if you have, that is, if the concentration of hydrogen ions are greater than the concentration of hydroxide ions, then we are saying the solution is acidic. If the concentration of hydroxide ions are more than the concentration of hydrogen ions, then we say that the solution is basic in nature. Okay, so this brings up the concept of a solution being acidic and a solution being basic. Okay. And this actually brings us to defining the terms, okay, an acid, because we are saying the solution is acidic. So what is an acid then? What is an acid? There are three ways in which acids can be defined. One is called the Arrhenius definition of an acid. One is called the Bronsted-Lowry definition of an acid. One is called the Lewis definition of an acid. If you are doing organic chemistry, you realize that the Lewis acid are very key. Okay? The Lewis acid and the Lewis bases are very key. Anything that is electron deficient, we might call it a Lewis acid. Anything that is electron rich, we might call it a Lewis base. But in biochemistry, the definition that is more helpful and more useful to us is the Bronsted-Lowry definition of an acid. These are just two scientists that came up with a definition. Okay. In this theory, acids are defined as an acid is a substance that donates a proton. And a base is vice versa, of course, is a substance that receives or accepts a proton. By a proton, we mean hydrogen ion. Hydrogen ion. Okay? Arrhenius says that any substance dissolved in water produces hydrogen ions as the only positively charged ions. That is an acid. Whereas a base is any substance which, when dissolved in solution or dissolved in water, produces hydroxide ions as the only negatively charged ions. A Lewis acid is a substance that accepts a pair of electrons. A Lewis base is a substance that donates a pair of electrons. But in biochemistry, what is useful is a Bronsted-Lowry acid, which is and base, which is defined in this way. Why talk about bases and acids? Okay. When you remember, this is biochemistry, and we're looking at the constituents of a cell. Most of the constituents of a cell exists as acids and bases. Not all, but most of them, in one way or the other, they act as acids and they act as a base. Secondly, the environment in which these substances are dissolved will be either acidic or basic. They may be neutral. There may be a solution which is neutral. Okay? So, in a cell, in a compartment in a cell, the environment in which substances are dissolved may be acidic, may be basic, or may be neutral. Secondly, substances themselves, the constituents of a cell, may be acids or bases. So it's important for us to understand what a base and what an acid is. Okay? Therefore, we can say that hydrogen ions in solution will tell us the state in which the solution is. Is it acidic or is it basic? If you have more hydrogen ions, then it's acidic. If you have less hydrogen ions than hydroxide ions, then it is basic, as it were. Okay. Now, when you look at these numbers, if you look at the concentration, okay, the concentration of hydrogen ions or hydroxide ions, 1.0 times 10 to the power minus 7 is very small and very user and friendly. Very small and very user and friendly. So Solesens, okay, a Swedish scientist, came up with a term or with an expression that expresses the concentration of hydrogen ions in such a way that it is a user-friendly value. This is not a very user-friendly value in terms of when you are doing calculations. Okay, the values are too small and hence very user unfriendly. So Solesens came up with a way of expressing hydrogen concentration that is user-friendly to you and me. Okay, he actually introduced minus log. Okay, introduce minus log, okay, to hydrogen ions. Okay, minus log is the same as the log is the same as the log of 1 over hydrogen concentration. Okay, so we are just introducing minus log in front of hydrogen ions. Okay, so if we say minus log of 1.0 times 10 to the power minus 7, okay, try to calculate that. Okay, try to calculate that. Okay, if you do the calculation, this will give you 7. This will give you 7. Okay, that will give you 7. Okay, so we are saying minus log of hydrogen concentration is 7. Is this user friendly? Yes, it is. Is 1.0 times 10 to the power minus 7 user friendly? No, it's not. But this is. So in other words, we are just expressing hydrogen concentration in a way that is user friendly. Now this parameter is called the pH. Okay? So in biochemistry, when we introduce log to any parameter, it becomes P, that parameter. If we say minus log Michael, then it becomes P Michael. If we say minus log Peter, then it becomes P Peter. If we say minus log Gelita, then it becomes P Gelita. Okay? So pH is just a way of expressing concentration of hydrogen ions in a user-friendly manner. Okay? Right. So similarly,